Right, so this is the second part, and we shall come to linear processes which are done in an iterative way. So the idea is again very simple. So let's have a look. The idea is extremely simple. So we deal with configuration space, and a vector there will be something like at the nth position or n time. It will be something like x1n up to xkn, so a vector in R to k, and we shall have simply a rule which says that n plus 1 simply is some matrix times xn, and the matrix is always the same matrix, constant matrix, and of course it must be a matrix of the rank k, well, not rank but size k times k, right? So just to stay in Rk, so you just multiply it by a matrix. So you see that if we start with x0, then the nth value will be a to n times the initial condition. And actually we have seen already one such thing, right? Because imagine what we had with the linear recurrences with constant coefficients. So we simply took a vector yn, which was of this kind, that was, well, and we sort of remember the k plus 1 things, right? So the values of xn, well, the k previous ones, so that's the k values we need, and then we compute the yn plus 1, which is just remembering all but the very last one and providing the new one. And how did we come from the yn to yn plus 1? It's just by multiplying it by the matrix A, right? You see the first line of the matrix just gives you the linear recurrence which produces the xn plus 1, and all the others are to be copied but shifted by 1, so you have the ones below the diagonal. And of course now we know that seeking for the solution in the shape of lambda to n means that we want to find eigenvalues of the matrix, right? Because that's exactly what it means. So if we knew that the solution, if we knew that that yn plus 1 is obtained, well, the xn plus 1 is obtained from xn by multiplying by lambda, right? To get the lambda to n plus 1, and copying all the previous ones means that you simply multiply all the vector by lambda. So that's it. And now it's a simple exercise to compute the characteristic polynomial of this matrix, right? So that's what we did very recently, and you find out that it's exactly the characteristic polynomial which we dealt with in the previous video, right? So that's only another way how to see that actually it was wise to try to go that way, right? Because whenever you have something which deals with matrices, it's good to know that you understand the polynomials, right? So that's what's written here. That's the characteristic polynomial. And now the nice thing is that you see immediately that if you really iterate, what does it mean? So if you would be able to decompose the original vector into eigenvectors, linear combination, so that's the case where the matrix is diagonalizable in some reasonable coordinates, which we did in the last couple of weeks, then automatically you end up with the fact that the big lambdas in absolute value dominate, whereas the small ones will sort of relatively disappear. In particular, if they are in absolute value less than 1, they completely disappear via the iteration. And that's because if you look for eigenvalues and eigenvectors, then if a times x equals lambda times x, then ak times x equals lambda to k times x, right? So you see that the eigenvectors remain the same, whereas the eigenvalues are appearing with the case powers. And that's a very nice observation, and it also shows how useful the eigenvalues and eigenvectors are. And let's move on to a slight modification. Just have a look at this matrix. So that was the linear recurrence, the absolutely simplest one. And we mentioned already that it could be also seen as a population growth model. But there are better population growth models which are quite popular and successful in sociology, and that's the Leslie model for population growth. And here the matrix will be very similar, except you have at the first line you have something related to the fertility, because you imagine that your configuration vector is saying how big individual cohorts in a population are. So you have simply population split into cohorts, like the people say up to so 0 to 15, 15 to 30s, and so on, right? 30 to 45, 45 to 60, 60 to 75, and more than 75. And that would be just your number. So I don't remember how many it was, but m was not too big. And the fertility would say how many of new kids appear from that cohort in the next year, right? Whereas, within the 15 years, because the cohort just moves. So in 15 years, how many, right? And the tau are the survival rates. So because that says how many, in the recurrence we simply copied what was before, and now not everybody survives, so you have the survival rate. And this is actually behaving quite similarly as the recurrence procedure. So there is some say intuitive observation what we can expect from the characteristic polynomial, seeking for the eigenvalues and eigenvectors. But actually there is a quite nice consequence, right? So imagine that's what I told already before. So imagine that we start with the state vector, so in the beginning, and expect that we can decompose it as sum of eigenvectors. And then the case version of the state vector will be simply this. And so you see if all the lambda i's are less than 1 in absolute value, except the first one, and the first one would be a little bit bigger than 1 or exactly 1, then you know how your population will grow. And there is an example here. So this is obtained from some real world situation, breeding of sheep in New Zealand. So you see you have 5 cohorts, say by 1 year. So the eldest one do not give any new breed, and no one lives longer, right, than 5. And you see these are regular numbers observed at some farm. And if you compute the eigenvalues, which you could easily do in Sage or anywhere else, you get the first one will be 1.03, so it means something like 3% of growth. There will be 1 of 0, right? That's clear because you have this 0 column here, and all the other ones are in absolute value strictly smaller than 1. So the absolute values are here. And so you see that if you iterate, then the relations in the cohorts will approach quite fast the relations in the dominant eigenvector. And if we choose the eigenvectors are determined up to rescaling by constant, so we can rescale it so that the sum of the values will be 100. So you see here, you see the percentage. So there will be 30% the sheep in the first cohort, 27 in the second, 21 in the third, 14% in the fourth, and 8, well, outliers will be still surviving in the 5th year. And so you see, and now the task could be, for example, that would be a nice task for an exam, if we had written exams. So just tell how to decrease tau 2, this one, so that the dominant eigenvalue would be 1. So it means we would just eat some of, or send to butchers some of the sheep which are 1 year old, and we want to do it in such a way that the whole situation is stable. So if you add some unknown constant here and compute, then you simply solve the equation to make this 103 to 100. And that's it, right? So this is a nice illustration. And how do we know that it will mostly just end up this way, so that the eigenvalues will behave this nice way? By the way, this Leslie model was used already, I don't know, 50 or 60 years back by sociologists to explain the fact that if you look at population, say human population, then the relative ratios between the cohorts are very stable, independent of whether the whole population grows or descends. And that's the reason, right? That's the reason, because it's just the same as the relation between the eigenvectors, the components of the eigenvector. Right. So there is a theory which explains why this happens. This is something worth looking at. You see my emoticon for the beginning is quite nice, socializing. It's called the Perron-Frobenius theory. I am dealing with only part here, and here is the Perron theorem, right? So if we deal with special case of matrices where the matrices are having only non-negative reals as components and some power of them. So you imagine if you have a matrix which has got only non-negative elements, then iterating the matrix, counting the power a to k, there will be more and more positive elements there, because whenever some of those positive ones meet, they will add something, right? And we shall deal here only with the so-called primitive matrices where some of the power is already only positive, right? And then we can say that there exists an eigenvector associated with the dominant eigenvalue, and the dominant eigenvalue is the spectral radius, which is eigenvalue, right? So remember, spectral radius was the absolute values of all the eigenvalues. That was the spectrum of the matrix. And here the theorem says that the biggest absolute value of the eigenvalues is itself an eigenvalue, and it's of multiplicity 1, and all the others are strictly smaller in absolute value. And moreover, there exists an eigenvector such that all the components of the eigenvector are positive. And then taking this eigenvector, we get to the conclusion. And you see, this is something I consider as a difficult proof. So for those of you who like these kind of challenges, just go through and try not to lose your teeth. For others, just skip it. But the claim of the theorem should be very easily understandable. So you see, the proof takes some time, but there are some very nice simple corollaries. The corollaries number 1 is that if you have a primitive matrix and if you take any eigenvector with all coordinates positive, then it must be the dominant one, and the spectral radius lambda bigger than 0 must sit between the sums. So you simply can take the columns and you sum them just by columns, and the minimum of the sums and maximum of the sums form an interval where the lambda must sit in. That's a very important and very useful theorem, right? So for example, if I go back, so this very matrix was not primitive, but if I put anything slightly non-zero here, like an error, so I don't know, 1 in times 10 to power minus 30, right? So it would be already primitive. So we can, numerically, we can just ignore the fact. And then you see the sums, right? So the sum, so here is 1.2 is the biggest, 1.5 is the biggest sum, and 0.95 is the smallest sum, right? And so this dominant value must be between those, and it is. Right, so that's the Perron theorem. And I think that's it for this video. One observation left though, of course, as soon as the matrix is diagonalizable, and so we end up in this case, so seeing that the x, or the initial condition, can be written as a linear combination of eigenvectors, then we see that all the other ones very quickly disappear. But what about the case it's not diagonalizable? And that's one of the reasons we shall spend some time with what we shall call in the future Jordan canonical form of the matrices. So we shall see that actually the failure to be diagonalizable comes with the fact that there are subspaces where instead of being eigenvector, you have a chain which is similar to eigenvector, and so therefore there will always be a decomposition which will simply make sure that the things are disappearing with iterating, but they disappear a little bit slower. So you will have several jumps to come to the point where it would be if it was directly an eigenvector. So that's just a promise that we shall settle this special case later. It's not left out of our horizon.